All right, so this lecture will introduce you to the idea of variance and variability. This is really key to statistics, so we'll use this information a lot. When we talk about variability, it's one of the basic descriptors of what data look like. Typically, we combine variability with measures of central tendency. So the chart below shows the differences in variability scores for three different distributions, which all have the same mean. They all have the same n or number of samples, but you can tell that they look very different. So sample A, the distribution is spread out, while in sample B, it's more clustered together. And in sample C, the distribution is not spread out at all. So all of the scores are the same. So variability is an attempt to kind of capture these kinds of differences. The normal distribution is kind of the way data is ideally distributed. Variation, you can see variations in the normal distribution where sample A has a very narrow range of scores, sample B has a wider range of scores and is less peaked, and sample C has an even wider range of scores and is flatter with fewer scores around the mean and more scores in the tails of the distribution. So again, the purpose of looking at variability is to describe the distribution in terms of how clustered together or spread out the scores are, and also describe how well an individual score or group of scores represents the entire distribution. So variability is really important for inferential statistics, and when we use samples to ask questions about the population, we need to know about the variability. So there's three basic measures of variability: the range, which is the simplest, and then variance and standard deviation, which are connected. So the range is the distance covered by the scores in the distribution. So generally, the range is the largest score, or X max, minus the smaller score, or X min. So this works really well for precisely defined upper and lower values. When the measure is continuous, we need to take into account the upper real limit and the lower real limit. So remember, we talked about with continuous variables, if you have a 5 on a continuous scale, the 5 can actually be anywhere from 4.5 up, which is the lower real limit, to 5.5, which is the upper real limit. So we need to take this into account. And so the problem with the range is that it's completely determined by the upper and lower limit. So if, for example, we have extreme values, like if we look at the town of Wise data, there was one person saying that they have an 8-hour commute from home to Wise. It's really going to heavily affect the range. So we can see how you calculate the range. Again, with discrete data, it's pretty easy where you have the difference between the minimum and the maximum. But if we have continuous data, we've got this example here of a bunch of different scores. So X max is 12. The highest number in this sample is 12. So the upper real limit of a score of 12 would be up to 12.5. The X min, the lowest score in this sample, is 3. So the lower real limit would be 3. So the lower real limit of 3 is 2.5. So the range is the upper real limit of X max minus the lower real limit of X min. So the range would actually be 10 for this. Okay, so standard deviation is the most important and most commonly used measure of variability. And what standard deviation is the average or standard distance from the mean. So the question is, are scores clustered closely to the mean or widely scattered? And the concept is pretty straightforward, but the calculations get a bit complex. But if you follow the logic, it makes sense. Before we get there, though, there's a couple of important notes about notation. So here we really start to see differences in calculation between if you're calculating for a sample versus a population. So we're going to start with the population because it's simpler, but we have to make some modifications for a sample. So there's some symbols that are the same whether we're referring to a population or a sample. The data score, so it's going to be X. Summation, the uppercase sigma, Greek letter sigma is summation, and that means the same thing. We've covered summation notation in the first chapter. But there are some symbols that are different for populations and samples, even though they represent the same concept. So for the mean, mu this is the Greek letter mu. This is for the mean of the population. For the sample, you'll see the sample mean represented as X bar or as an uppercase M. Either one can indicate a sample mean. Mu is always a population mean. For variance, this symbol right here is the lowercase Greek letter sigma. Okay, so for a population variance, sigma squared indicates a population variance. For a sample, lowercase s indicates, s squared indicates a sample variance. Variance is the standard deviation squared, so the standard deviation is related. So standard deviation for a population is a lowercase Greek sigma, and standard deviation for a sample is lowercase s. So for the population, standard deviation is sigma, variance is sigma squared. For a sample, standard deviation is lowercase s, and the variance is s squared. For the number of data, so the number of scores or the number of subjects, for population, it's uppercase N. For a sample, it's lowercase n. So just get familiar with this notation. Okay, so we'll walk through an example of how this is calculated in class, but I want to get you kind of the basic ideas. And so a deviation is the distance of a score from the mean. And you can see that I'm using mu here, which indicates we're talking about population means right now. So every single score, every X has a different deviation, which tells us how far it is from the mean. So the mean is always the reference point that we use for everything. And we calculate the deviation by subtracting the mean from that score, from the X. All right, so if we have a distribution, a population distribution with a mean of mu equals 50, if we have an X of 53, the deviation score for that specific score would be 53 minus 50, or 3. If we have a score of X, then the deviation score would be 45 minus the mean of 50, would be minus 5. So when we look at these deviations, the number and the sign can tell us, so the sign, whether it's positive or negative, tells us whether the score is located above the mean or below the mean. So I can see that 53 is located above the mean because it's positive, while 45 is located below the mean because it's negative. And then, of course, the actual number tells us how far it actually is from the mean. Okay, so when we're looking at these deviations, the mean is the point where scores are balanced regarding the distance from the mean. So the mean of the deviations is always 0. You'll have an equal number of deviations above the mean, and below the mean. Okay. So you can kind of think of this as a seesaw, and the point where the scores are all balanced in regard to how far away they are is the mean. So when you add up all of your deviations, just when you add up the plain deviations, they will always equal 0 because you have an equal number above the mean and below the mean. So in order to get it so that when you add up these distances, we don't get 0, to make the negative values go away, what we can do is square them all. And so this requires the sum of squares. And so for the sum of squares, what we're trying to do is adding up all the deviations. So the sum of squares, if we remember our order of operations, the first thing we're going to do is parentheses. So we're going to take each individual score and subtract it from the mean, get our deviation score. Next thing we do is exponents. So then we're going to square each one of our deviations, and then we'll add them together. Okay, so you'll do this just like we have with other frequency distribution tables, although in this case, this isn't a frequency distribution, it's just a list of the scores. We've got each of our scores here. The sum of X is 20, if you add them up. And then we can calculate deviation scores for each one of our scores. So we subtract the mean of 4 from each one of our scores. So you can see that the scores above the mean are positive, the scores below the mean are negative. If we add them all up, all of our deviations, we get 0. So we're going to square each one of our deviations. 3 squared is 9, 2 squared is 4, and so on. So now what we can get is the sum of the squared deviations. We've got our deviations, we've squared each one, now we can add them all up. And so our sum of squares, which is the sum of the square deviations, equals 24. So the most intuitive way to do this is go through and calculate the deviation, square it, and then add it all together. This is called the conceptual formula. You can also use the computational formula, which can save you a few steps, and you will get the same answer. So we'll do an example of in class. But if you use the sum of X squared, so you square each score and then take the sum and subtract it from the sum of X and then square that divided by N, it gives you the same thing. So we'll go through an example in class, but you'll get the exact same thing. Sometimes the computational formula is a little more efficient. So I just want you to be aware of that. So we've got our sum of squares, but we want to know what the score is for each individual, or the average score. So variance is the next step that we're going to get. And variance is essentially the average squared deviation. Okay, so just like the mean is the sum of X divided by N, the variance is the sum of squares divided by N. Okay, so again, we're talking about the population, so we're using sigma squared equals the sum of squares divided by N. Now, we don't really care about things in terms of squared units. We want to know this in a meaningful unit. And remember, the ultimate goal here is to try to find the average distance from the mean. So we want it in the same metric or the same units as the original scale. So to get back to the original scale, or the original units, we're going to take the square root of the variance. So the standard deviation, or sigma if we're talking about the population, is the average deviation from the mean. So standard deviation is computed by taking the square root of the variance. So sigma equals the square root of sigma squared, or you can also look at it as sigma is the square root of the sum of squared divided by N. So again, we don't really care about the average square deviation from the mean. What we want to know is the standardized version, or the average deviation from the mean. So that brings us back to our original scale and corrects for the fact that we had to square all of the deviations to get them positive. And so what the standard deviation really does is gives us a measure of the average distance from the mean. A bigger standard deviation indicates that there's more variability in a set of scores, or they're more spread out. Okay, so remember that the difference between a sample and a population is that a sample is a selection of people or individuals from our population, but not all of them. And so what that means is whenever we're calculating things for a sample, we need to be aware that the sample could be biased. And so the sample variance is a biased estimator of the population variance. since we don't have data from the population, the sample variance is calculated from the data that and uses the sample as an estimate. So we can actually statistically take this into account. Practically, what this means is that we have to adjust our formulas a bit. Okay, so generally the formulas are very similar, and the concept is the same for both populations and samples. So the deviation and variance for the sample is similar to that of the population, but do note that the symbols and the number scores are different. So really the biggest change is a symbol, and rather than dividing by capital N, we're dividing by n minus 1. So here the deviation score for a population, it was x minus mu. Here for a sample, the deviation score is x minus x bar, or you might also see x minus capital M. For the conceptual formula, for the sum of squares, we've got x minus x bar instead of x minus mu. Again, essentially the same. For the computational formula, again, we're dividing by lowercase n instead of uppercase n. And then for the sample variance, the big change to kind of how you calculate it for a sample is note that capital N, so the full number, is replaced by n minus 1. This is to take into account degrees of freedom, which is this very abstract concept, which we'll discuss a little bit later. But for now, just note the change in the formula. When you've got a sample and you're calculating the variance, you need to do n minus 1 as opposed to capital N. And then our sample standard deviation is the square root of the variance. But again, variance for a sample is s squared. So it's the standard deviation for a sample is s. And again, we're dividing by n minus 1 instead of n. So there's a few ways that we can shift scores, and we can kind of see how they affect the standard deviation. So again, remember the standard deviation is a measure of how spread out the scores are in a distribution, the average distance from the mean. So if we were to add a constant to each of the scores, so if we added 1 to every single score we got, the mean would change. The mean would go up by 1, but the standard deviation would not change. Where the mean is, the center point of the distribution does shift if you add a constant to every score, but the spread of the distribution doesn't change. If, in contrast, we multiplied each score by a constant, so if we multiplied each score by 2, the standard deviation would increase by the multiplier. Okay, so if we multiplied each score by 2, the standard deviation would double. Okay. S, so the standard deviation is unbiased if its average value over many different samples approaches sigma, which is the standard deviation for the population. But we can't be sure how biased or unbiased our standard deviation for our sample is, right? So S is biased, the standard deviation for the sample is biased if its average value over many different samples doesn't approach the standard deviation for a population. We can't know whether our standard deviation is biased or unbiased. And so one of the reasons that we divide by n minus 1 is to kind of correct for this potential problem. Okay. I also just want to note, because this is leading up to when we get to z-scores, we know certain pieces of information about how many people are within a certain standard deviation. So we know that roughly 70% of scores fall within one standard deviation of the mean. So at one standard deviation above or below the mean. We also know that about 95% of scores fall within 2 standard deviations of the mean. So 2 standard deviations above or below. And so with IQ scores that we know the mean is 100, and the standard deviation is 15, we can say with great certainty that about 70% of people will fall either 15 points below or above 100, and 95% of people fall within 30 points of 100, so between an IQ of 70 and 130. So we'll use this information later on in the class, and during class, we'll go over examples and walk through exactly how to calculate the standard deviation.